Bland's rule doesn't cycle, but we obviously have to write a proof before we can really assert that claim. Once we've written that proof, however, we will have enough to be able to assert that the simplex method always terminates. And in fact, because we know already that there are three terminal states, which is the LP is infeasible, unbounded, or has an optimal solution, in all of those cases, if the simplex method reaches one of those end states, it provides us, in the form of its final dictionary, with a certificate of that status. So actually, all we need between here and being able to show that every linear program has a solution that the simplex algorithm can find is to show that the simplex algorithm doesn't cycle. Once we prove that Bland's rule, when used as the pivot selection rule, doesn't cycle, we will be able to state and prove the fundamental theorem of linear programming. And mercifully, the proof of that theorem will basically be a couple of sentences long, because we can use the simplex method by the time as long as we can prove it doesn't cycle, we can use the simplex method as a device in the proof. We can use the fact that the method always terminates to essentially write the proof for us. But of course, first we have to prove that if I use Bland's rule, that there will never be a cycle. So the proof itself is really ugly. The reason it's ugly isn't really because it's conceptually challenging. It's mostly because we're fighting against notation. So we're going to need to we're writing a proof that involves discussing what the simplex method does, and it's going to require us describing two different dictionaries, which means we have to give a huge number of different names to different variables and then juggle those names. So that's why I think it's only difficult for notational reasons. The proof does do a couple of clever things. I like it because it is a proof that uses pretty much only algebraic first principles. But I want to go over the insights that it's going to use before I jump into the proof itself, so that way we can see those insights independently and maybe appreciate what's really going on there before we dive into the proof. So the first insight has to do with what is really happening during a cycle. So if I have some dictionary D1, and I perform some sequence of pivots, and I end up back at D1, well, obviously, the objective value of a dictionary is encoded into the dictionary. It's a constant that's part of the dictionary, which means if I start at D1 and I end up back at D1, the objective value will be the same here as it is here. We also know that under no circumstances will the simplex method perform a pivot that lowers the objective value. Now, there's nothing that precludes us from doing that kind of pivot. So a dictionary and the simplex method are two different things. We are allowed to use dictionaries for whatever reason we want, but if we are running the simplex method, it will never perform a pivot that lowers the objective value. And therefore, we know that if a sequence of pivots takes us from D1 back to D1, that the objective value has to have remained the same the whole time. Because if the objective value goes up somewhere in the middle, how does it go back down to get us to D1? So we know that. We also, of course, understand that because we know that cycling is the result of degenerate dictionaries, and if I perform a degenerate pivot, then the objective value will remain the same. That's sort of by definition. And so what this is saying, the insight is any variables that enter or leave while the algorithm is cycling, so that is between D1 and D1 again, any variables that enter or leave must actually have the value 0 the whole time. So it's not just saying that any variables that enter or leave must be 0 when they enter or leave. It's saying they must be 0 the whole time, even during the iterations where they are not entering and leaving while the cycle is in progress. So a variable might not have to be 0 over here before we get into the cycle, but once we get into the cycle, that variable has to be 0 the whole time if it enters or leaves at any time during the cycle. There are a few ways to justify this. So one observation, this is something we already know, is that if I'm in the middle of a cycle with respect to some pivot rule, so suppose I chose x1 as my entering variable, which meant that either w1 or w2 has to be the leaving variable. If I choose a variable to be the entering variable, the only reason a cycle is occurring is because every single pivot is degenerate. A degenerate pivot is one in which the leaving variable has the value 0. And we'll notice that if I chose x1 as my entering variable, then when I solve, I guess I could choose w1 as the leaving variable or w2. When I solve that basis row for x1, x1's going to end up looking like this. x1 equals 0 plus some stuff. So x1 will have the value 0. x1, of course, had the value 0 to begin with before the pivot because it was a non-basic variable. And so what this is saying is any variables that enter or leave, during the cycle, all I'm really doing is rearranging my dictionary, and any variable that enters or leaves during the cycle will have the value 0 the whole way through. Another observation to make is that during the period in which I am cycling, what I'm doing is standing at exactly the same vertex of the polytope and rearranging my bases. That's it. So the values of every variable actually stays the same for the entire cycle. I've just changed which variables are in or out of the bases. And for a couple of reasons, that implies that any entering or leaving variable has to be 0. Because if a variable ever enters during the cycle, it means that variable was non-basic at some point during the cycle. And if it was non-basic, it must have been 0. And therefore, it'll still be 0 when I take it out, when I put it in the basis, and then eventually when the cycle continues, we'll go back and become a non-basic variable again. So the key thing for insight number 1 here is that it doesn't matter where you are in the cycle, any variable that enters or leaves during that cycle will be 0 the whole time. Insight number 2 is a bit more complicated. It sort of has 2 facets. The first one comes back to a property of dictionaries that I emphasized even when we first introduced dictionary notation. And that property is that a dictionary, deep down, is just a way of representing a system of equations. That's it. Any meaning we ascribe to it is because we've chosen to interpret it a specific way. So fundamentally, the only difference between a dictionary and a system of equations is that I've drawn this horizontal line. I mean that's it. And so we can use that to understand certain things about the properties of the system of equations. If, for example, I pivot x1 out of my basis and I get some other series of expressions, it's actually the same system of equations, just rewritten in terms of different independent variables. And so one example I will use x1 for this, but notice how both of these 2 dictionaries, it turns out these 2 dictionaries not only correspond to the same LP, they actually correspond to the same vertex of a polytope. So most of what insight 2 is getting at actually applies for any 2 dictionaries of the same LP, even if they're at different vertices. But for the sake of keeping us focused, let's think about the case where you have 2 dictionaries that both correspond to the same vertex of the polytope. So that would mean that I can obtain one dictionary from the other with a sequence of degenerate pivots. So notice how in the dictionary on the left, it says x1 equals this. So a property of this system of equations is that x1 equals 2 minus w1 minus x2. Okay, that equals x1. Over here, the same system of equations rewritten gives me this expression for x1. So 2 minus 1 half w, I gotta practice my w's, plus 1 half w2 minus 1 half w4. Okay, so it's giving those 2 expressions for x1 for the same system of equations. The key thing to observe is these 2 dictionaries are different ways of expressing the same relationships. And that means that any identity I see on x1 or any other variable applies in both of them equally, which means that I'm not just saying both of these equal x1, but by the transitivity of the equal sign, I'm saying that they both equal each other. And that's a very important observation for the proof. The proof will hinge on this kind of logic. And this is valid. This is an identity. For any assignment of variables within this system of equations, this identity is guaranteed to hold. And so I can draw inferences based on this identity if I want to. Now keep in mind, there are certain constraints that we place on dictionaries that are artificial. One constraint is that we assume non-basic variables are always 0 during the simplex method. Okay, fair enough. We can do that during the simplex method. The property I'm stating here isn't specific to simplex or anything else. It's just saying if I have 2 dictionaries representing the same system of equations, regardless of why I have those dictionaries, these relationships hold. And so in this case, I mean, we know that already. I've been saying that since the beginning, and the reason I've been saying that is, in fact, because I knew we would later need to use properties like this in a proof. And remember, the convention that all non-basic variables are 0 is a convention. The dictionary doesn't imply that. It's the way we use a dictionary that implies that in our use. And in the proof, we're going to use, at a couple of points, we're going to use a dictionary just as a list of equations. We're not necessarily going to enforce these requirements that all the variables that have columns are always set to 0. And notice, this is pointing out, notice that these 2 dictionaries are not just dictionaries on the same LP, but they actually describe the same variable assignment. They are 2 dictionaries describing the same vertex of the polytope. There's this other bit, this is illustrating the relationship I just pointed out, but it's doing it on the objective function expansion. So remember that because these 2 dictionaries both give different expressions from the objective function, they are effectively stating that this expression equals that expression. I've given the two objective function expansions different names, zeta 1 and zeta 2, only so that way I can refer to the expansion in one particular dictionary, but they really are the same thing. They're just two expressions of exactly the same quantity. Now there's this aspect. So this is the second part of the insight, which is, okay, so suppose that I do say, fine, for now, w1 equals 0, x2 equals 0, x3 equals 0, the typical way that non-basic variables work. That's the way the simplex method would treat them. But really what this is saying is, for any assignment of w1, x2, and x3, these are the values of these four variables. So if I change w1 to be 5 and x2 to be 2, then x1 will be 2 minus 5 minus 2. It applies regardless of what values I give, w1 and x2. Now, we don't do that in the simplex method, but we can do that if we want to in general. So suppose I decide to do this. Suppose I say we will begin with all of our non-basic variables set to 0, but then I'll pick some value y, which is greater than 0, and I will set x3 to equal y. Okay, so the simplex method wouldn't do this, but the dictionary system of equations, I can do whatever I want. So I set x3 to equal y. Now, with all other variables held at 0, what does that give us? Well, it means the objective value is now 2 plus y, because y is obviously greater than 0. Previously, the objective value was just 2, because x3 was set to 0. Similarly, w2 is now equal to 0 minus y. And what I want to get at here is that this dictionary is another way of visualizing the same set of relationships. So shouldn't there be a way for me to model this change in the other dictionary? And the answer is yes, although it's not obvious. I can't just over here write, oh, okay, x3 equals, well, obviously that's not going to give me what I want. I want to see how applying this change reflects on the entire system of equations. And to do that, I have to be a bit more careful. So let's instead just think of that objective value. So on the left, the objective value comes to 2 plus y. Is there a way I could sub in something into this thing, keeping all of the relationships as they are, such that I can verify that this is indeed an expression of exactly the same function as what I have over here? And the answer is yes. The issue is over on the right, my objective function is stated in terms of w1, w2, and w4. Now we know that we're keeping w1 at 0 because it's non-basic over on the left. The problem is w2 and w4 might not be 0. So if I move on, just simplifying what I had on the previous slide, w2 and w3 and w4 become 0 minus y, 4 minus y, and 0 minus y. Previously, they were just 0, 4, and 0, but then I increased x3 to some positive value, and so now now that has to be factored in to the values of those variables. If I now take these expansions for w2, w3, w4, keeping in mind that w1 is being held at 0, then I get this. I can just sub those in to my objective function on the right to get, okay, so w2 is equal to 0 minus y, and w4 is actually also equal to 0 minus y. And if I simplify that a bit, obviously 0 minus y is just negative y, and so 1/2 times negative y would be negative 1/2 times y, and then these two cancel out. So now I've got 3y over 2 minus y over 2, which just equals y. Okay, which, wait a minute, that means the objective value would be 2 plus y, which is exactly what I had over here. Okay, so that is a way of sort of visualizing this. Really, these two dictionaries refer to exactly the same thing. If I make a change to a variable and I plug it into one dictionary, I can work my way backwards to see how the change is reflected in the other. And of course, all of the changes should be reflected evenly. Like any variable value that I get out of this dictionary should be reflected over here once I've done all the substitutions I need to do. And so the slide is going to explain that. It's going to do all the algebra I just did. There it is. It comes out to the same value. Okay, so we're going to return back to slide 37 and slide 34, I think, over and over again in the next few minutes. And I've actually looked into whether I can use on my drawing software, whether I have any hotkeys, let me skip back faster. And it turns out, nope, not unless I want to make a pull request or something. So I'll work on writing a plugin for the software later. Unfortunately, in the video, you're going to have to just watch me scroll back and forth. So here it is, the theorem. When I use Bland's rule to choose the entering and leaving variables, then the simplex method doesn't cycle. So I want to just elaborate a bit on this. So we know already that when I'm choosing my entering variable with Bland's rule, what I do is I figure out which variables have a positive objective coefficient. And among those, I then choose the lowest numbered one. That becomes the entering variable regardless of its coefficient. As long as it's positive, as long as it is a candidate to be the entering variable, I choose it as the entering variable if it has the lowest index among all possibilities. What about leaving variables? So in this case, I chose x3, I guess, as my entering variable. Okay. And then I notice that I've got something like, I don't know, we've got x10 equals 0 minus 3x3. x11 equals 9 plus 2x3. And then I guess I ought to do one more. Sorry that it overlaps the text here. x12 equals 0 minus 10x3. Okay, so among the possibilities, what are candidates for leaving variables? Well, we know that this, x11, doesn't impose any bound at all on x3. x10 and x12 both impose this bound here. x3 is less than 0, or less than or equal to 0. x3 is less than or equal to 0. And this is, maybe you can agree, there aren't going to be any other variables that impose a tighter bound than that. So both of these, x10 and x12, are candidates for the leaving variable. And that means there's a tie. How do we resolve the tie? Bland's rule says, in the event of a tie, always choose the lowest numbered one. So we would choose x10. It turns out that if we don't resolve ties in that orderly fashion, cycling could still occur. And we'll see in the proof that, in fact, the main insight of the proof comes down to how the leaving variable is chosen, not the entering one, even though we do tend to think that pivot selection is mostly about entering variables. So that's the key thing. If you were to use Bland's rule to choose the entering variable and then just sort of choose the leaving variable arbitrarily, a cycle would still be possible. But the theorem I'm stating is, if I use Bland's rule to choose both entering and leaving variables, then I will never see cycling. So how are we going to set this up? Okay, first, this is the proof, the same proof that Vanderbeek gives. It is identical. I have cleaned up the notation, but I don't consider that I've added anything to it other than that. I mean, it's actually the same set of steps. I've just tried to simplify notation a bit. We're going to notice in this course that I think I've got a few pretty fundamental differences of opinion with the way Vanderbeek writes proofs, because Vanderbeek's proofs tend to be very, very symbolic. So instead of just using different names for variables, the same name will be used over and over again with a bunch of strange symbols over it. So instead of just using A, B, and C, it seems like his proofs tend to like to use A hat, A star, and A tilde, which in my mind does not make things any easier. And we really need to make things easier, especially in a proof like this. So it is still a nice proof. It's sort of perfunctory, like it doesn't tell us that much about what's going on, but it does definitely make the case. The other book does, I think, have a proof of this, but it involves a bunch of things that we don't necessarily have, so it requires some extra knowledge. The advantage of this proof is all we need to know about are dictionaries and the simplex method to write the proof, and, you know, have a certain amount of a thick skin, I guess. So it is the same proof. The one I'm going to give is the same proof that Vanderbeek gives, but I have changed the names of variables so they're not directly congruent. The proof itself is nasty. The reason it's nasty is because of all the notation. It's not actually because of advanced algebra or anything else. Those insights I mentioned earlier factor into it, but really it's just an annoying proof. There's just lots of stuff to keep track of. And as I said, I suggest you watch this, and then you may want to keep the slides up on the side to follow along with them, because I'm going to have to keep flipping back and forth. Okay, so let's consider a linear program with n optimization variables and m constraints. And that means that our initial dictionary might look something like this. So 0 plus some number times x1 plus and all the way up to cn times xn. And then normally our dictionary would say w1 equals, that's our first basis row in our initial dictionary, w2, all the way down to wm. Okay, now as you can see, I hate drawing W's, I'm terrible at it, and we know that if a cycle ever were to occur, it wouldn't necessarily occur at the very beginning. I could run 5,000 pivots and then hit a cycle. After running 5,000 pivots, I have no idea where all the W's and where all the X's are going to be. In fact, it doesn't really make any difference to me. They're sort of the same. There's no real significance to the W variables during the iterative process. I only care about the difference when I'm reading off the optimal solution, or when I'm creating the dictionary. So as a notational device to make our lives easier so that we don't have to differentiate, because once we get to a cycle, they're just going to be mixed together, the W's and the X's. What I'm going to do is renumber all the W variables as X variables. So I'm only going to have x variables when I'm done. So I have x1 up to xn are my optimization variables. I will define xn plus 1 to be w1, xn plus 2 to be w2, and then finally xn plus m to be wm. And that way, I no longer have to worry about w's. All of my variables are x's, and they're just numbered continuously from 1 up to n plus m. Okay, that's the first modification I'm going to make. Okay, now, suppose that with this LP, this arbitrary LP in n dimensions and m constraints, suppose that even though I'm using Bland's rule, it cycles. And we get at some point in the algorithm, not necessarily at the beginning, but at some point while the algorithm is running, we hit this sequence of k dictionaries that takes us into an infinite loop, that takes us into a cycle. So d0, d1 up to dk minus 1, and then back to d0 again. And then that just keeps going around forever and ever. We're going to show that this leads to a contradiction, that if we're using Bland's rule, it is impossible to reach this state. And to do this, we have to consider, so Bland's rule is about choosing the lowest numbered variable. So it shouldn't surprise us that the proof is going to hinge on considering the index of particular variables. And we're going to eventually charge forward into a contradiction, but it's going to be pretty rough terrain between here and there. And the next slide, I think, is a pretty good demonstration of why. So let's take, we know that during this cycle, so I've got d0, that goes to d1, and then I keep running until I get to dk minus 1, and that takes me back to d0. Okay, so a bunch of pivots got performed. Clearly, at some point, at every specific step that I take, so d0, d1, d1, d2, I'm modifying the basis of the dictionary. So the basis of d0 is not going to be the same as the basis of d1 because I performed a pivot. Therefore, it's reasonable to assume, because the cycle has to have length at least 1, it's reasonable to assume that at some point during the cycle, variables enter and leave. Now, I know that's an odd point to make. Of course they do, Bill. The reason I want to make that now is because I want to make it crystal clear later that the only reason a contradiction could have occurred, the only assumption that we really made, was that a cycle existed. That's it. That is the only thing we assumed, that there was a cycle. Everything else followed from that. So the first thing is, it's reasonable that during that cycle, at least one variable enters or leaves. Okay, so let's define xd to be the highest numbered variable that leaves the basis at any point during the cycle. Now we know that if, for example, xd left the basis here, by the time we get back to d0 at the beginning of the cycle, xd is in the basis again. Otherwise, how would it leave at d1? So it's reasonable to assume that any variable that leaves the basis during the cycle also enters the basis at some point during the cycle, because otherwise, how would it be set up for the next iteration of the cycle? So this is true in general, not just of xd. Any variable that leaves or enters also leaves or enters at some point in the cycle. It has to both enter and leave, or it stays put for the entire cycle. Okay, now the next thing, which we don't need to get into, is xd is the highest numbered variable that leaves at some point during the cycle. I suppose it's possible that it could leave and enter more than once during the cycle. I don't really care. Let's just choose, we'll define the dictionary d out to be any dictionary where xd is the leaving variable. Similarly, we'll define d in to be any dictionary where xd is the entering variable. I don't care if there's more than one choice, just give me one of them for both. D out is a dictionary where xd leaves, d in is a dictionary where xd enters. Notice from the definition that I don't even care where these are in the cycle. They could be d0 and d1, they could be d1 and dk minus 1, who cares? The cycle just keeps going around and around. I just care that there are these two dictionaries. D out is where xd leaves, d in is where xd enters. Of course, we're going to want to keep track of the basis in each case. So we're going to define these sets. I want some compact way of representing what is in the basis at each step. So what I'll do is I'll define these sets of indices. We know now that all of the variables we're working with are x variables. So what we could do is define the basis to just be a set of indices. So for example, if b out equals, 1, 4, and 9, then that means the basis contains x1, x4, and x9. Now, it's also reasonable, because of what we know about dictionaries and a basis, that if I look at the basic variables in D out and I take the intersection between those and the non-basic variables, that would be an empty set, because a variable cannot be in both the basis and also not in the basis. That doesn't make any sense. So what I'm going to do on the next slide is I'm going to start drawing something that I'm going to refer back to later, which is that basically what the proof is going to do is it's going to use deduction to allow us to figure out what D out and D in really look like. So I'm going to make up a diagram here of what D out and D in look like, and we'll just we'll add pieces to it as we go. So here's D out, and over here we'll put D in. Okay, so what do we already know about D out and D in? Well, both of them are dictionaries. I guess I should draw the objective function, which means I'm going to need to make some attempt at drawing zeta. There's zeta. Ooh, well, that's about as good of a zeta as I'm going to get, so there we go. Okay, so I've got my objective function in both cases, and then D out is a dictionary where XD is chosen to leave. So what does that tell us about XD? Well, I guess if it's chosen to leave, it must be basic in D out. So right now we know that XD is down here. All right. Now, we also know from a lot of experience that the ordering of rows in the dictionary is arbitrary. I can rearrange them all I want. I'm going to adopt, just for the sake of my diagram, I'm going to generally adopt the convention that if I want to point out that a particular variable has a lower number than xd, I'll put it above xd in the basis, or to the left of it if it's non-basic. Okay, so din is a dictionary where xd is chosen as the entering variable. Okay, fair enough. That means that xd is non-basic in din. So that's what I know so far, that xd is non-basic in din and it's basic in d out. Now, because this is so complicated, what we're going to do, the next few steps are going to involve making deductions about each dictionary separately. So this slide is involving entirely d out, and later we'll see some slides that involve entirely d in. This was so confusing to me when I was making the slides that I can only imagine how confusing it would be to watch this. So what I've tried to do as a visual device is I've color-coded them. Every time you see a slide that's blue in the background, that's a slide that talks entirely about D out. So that's blue. Every time you'll see later, you see a slide, this is supposed to be red, you see a slide that's sort of this nice tasteful red, that's talking entirely about D in. And that's going to get complicated, but you can imagine things are really going to get unpleasant when you see a slide that's backed by white again, because that's going to involve both dictionaries at once. So what can we say about D out? Okay, well, in D out, XD is chosen to be the leaving variable, which means there has to be some entering variable, and it obviously isn't going to be XD. So what's it going to be? Well, let's call it XE. Okay, so we'll add that to what we know about the dictionary here. So there's XE. It's the entering variable in the dictionary D out. Now the next thing is the objective row of the dictionary. I mean, we know how the objective row of a dictionary typically looks. It'll be a constant, so we'll call that V. Let's update our diagram. V plus a linear combination of all the non-basic variables. And each non-basic variable has some objective coefficient. Okay, so fair enough. Like that's the usual way we represent the objective row of a dictionary. And we know that XE is the entering variable. And we also know, wait a minute, if XE is the entering variable, let's see. So my objective function is V plus, I guess I can use my previous slide. So I've called the objective coefficients in D out, I've used P for them. So P sub E would be the objective coefficient for XE. And there's V. What we know is that if XE was chosen as the entering variable, and I've represented this as a linear combination of just a sum of everything, if XE was chosen as the entering variable in dictionary D out, then we know that PE has to be positive. Because obviously, a variable with a negative objective coefficient is never going to be chosen as the entering variable. Okay, so we know that. That's one more deduction that we can make. Okay, so there's one thing. In general, of course, objective coefficients don't have to be positive. They could be 0 for all I care. But certainly, if I chose XE to be the entering variable, the coefficient on it has to be positive. Okay, so what else do we know? Well, first off, obviously, we already saw this, but if XD is the leaving variable, clearly it's in the basis. So remember that the basis is a set of indices. So the index D has to be in the basis. And similarly, since XE is the entering variable in D out, then it is non-basic. So it's in the set N, not in the set B. Now we have to come up with, we're going to want to relate xd to xe. So we have to write out, what does it mean? Like, what does the basis row for a particular variable typically look like? Well, let's see. So the basis row for xd would be, I don't know, some constant, b sub d, plus a linear combination of the non-basic variables multiplied by coefficients. Okay, fair enough. Let's add that to, so we know also that there will be some coefficient. It's numbered x, a, d, e. So I'm using a's to represent the coefficients on each basis row. And the row, so row I would be the row ai. So a, d, e times xe. So that's the basis row for my leaving variable xd. So we'll go update this. So it equals b sub d plus dot 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 plus a, d, e, xe. All right. But then we ask ourselves, okay, wait a minute. What does it mean for xd to be chosen as the leaving variable? So xe was chosen as the entering variable, and xd is chosen as the leaving variable. And I'm just going to skip back a few slides, and we'll stare at a dictionary that we've seen before. Okay, so here's this dictionary. So suppose I choose this to be my entering variable. And the question is, would either of these be leaving variables? And the answer is, of course they wouldn't. So we know already when we select our leaving variables, we only select variables that have a negative coefficient on the entering variable, because they're the only variables that place any bound on the entering variable. These two variables do not place a bound on the entering variable. W1 and W2 should never be the leaving variables because they do not bound x3 at all. So that allows us to conclude something about this coefficient ADE. So ADE, that has to be negative, because otherwise XD would not be chosen as the leaving variable. Okay, so we know this. That's the next deduction we can make. Now, let's spend some time talking about the way that dIn looks. So in dIn, xd is the entering variable. Okay, so the first thing we should do is observe there has to be a leaving variable. Let's call it xl. So let's write that in. There's xl. There it is. I have to be very careful to not make my L look like an E. There we go. So xl. And the objective row is, again, v plus a linear combination of stuff. And this is the same v that I had in the previous, in dout. And the reason for that should be clear, because both of these two dictionaries, dout and dIn, are just a degenerate sequence of pivots away from each other. Both dictionaries are part of this cycle of degenerate pivots, which means they are, both dictionaries refer to the same vertex of the polytope. And not only that, obviously we expect every dictionary in the cycle has the same objective value. That's part of insight number 1 from earlier. Therefore, if I treat the dictionary like a simplex dictionary, which is where I set all non-basic variables to be equal to 0, then I would expect that the constant in the objective expansion is indeed just v. I should also make sure I write this as zeta out and zeta in. Okay, so I have the same v on both sides. And then, let's see, so I have, as usual, a linear combination of my non-basic variables is the rest of the objective expansion. Normally, this doesn't contribute anything to the objective function, but it's in there. Algebraically, we care that the objective function is represented that way. And also, because in the dictionary dIn, xd is my entering variable, we're going to use q to refer to the objective coefficients in my dictionary dIn. If xd is my entering variable, then this coefficient, q sub d, has to be positive, for the same reasons that I had it on the left, which is that xd would not be the entering variable unless its coefficient was positive. So as you can see, we are able to make a few deductions about the way this works. We're also, if we care, we'd also be able to infer that the coefficient between xl and xd, the thing that would go here, that also has to be negative. It turns out that's not terribly relevant to us. All right. Now, obviously, as in the other case, the other objective coefficients, the other q values, do not necessarily have to be positive. They could be negative or 0. Although there is one observation that I could make, which I guess I'll make, the next slide makes it, but I want to point it out on this diagram here. So xd is chosen as the entering variable in this dictionary by Bland's rule. What does that tell us? Well, obviously it tells us that Bland's rule didn't select any variable with a lower index than xd. And we know if any variable with a lower index were available to be the entering variable, Bland's rule would have chosen it. Therefore, it's reasonable to conclude that everything else, everything between, I actually shouldn't do that. Everything between here, I'll say these are all negative qi. So I didn't want to use a negative sign because we actually expressed it as a positive summation. But all of the objective coefficients of the variables that are numbered lower than xd have to be negative in this objective function because otherwise Bland's rule would choose them as the entering variable. All right. The other thing I want to do in the meantime is, normally we only write out our objective expansion in terms of the non-basic variables. And I'm going to do that thing again. Sorry about it. I'm going to scroll all the way back to this dictionary we were working with earlier. So here's a dictionary. As we know, we have expressed the objective function in terms of this constant and a linear combination of the non-basic variables. My claim is that I can always write the objective function as a combination of all variables easily. What I do is I just add to the end all of the basic variables with a 0 coefficient. And you can see clearly clearly that changes nothing. It's a strange notational device. The reason that I want to do that is now I know that I could argue that now every single variable, basic or non-basic, has an objective coefficient, which makes it a lot easier for me to avoid having to juggle whether a variable is basic or not when I'm talking about its coefficient. The trick is all I do is I just define the coefficient for every basic variable to be 0, so that it has no real effect on anything. And that's what this slide here is doing. It's saying, because I don't want to have to worry about this summation in terms of n in, whatever that's supposed to be, the non-basic collection of variables, what I will do is I will just define, for every index j that is basic, so that isn't a non-basic variable, just define its objective coefficient to be 0. If I do that, I can just write the objective function in this much more pleasant notation as just the constant plus a linear combination of all variables, not just the non-basic ones, although only the non-basic ones end up actually having a non-zero coefficient on them. So I'm doing that. I don't need to do that in d out, it turns out. I only care about this in d in. We'll notice that although we're able to deduce a lot of things about both dictionaries, the set of deductions we make isn't symmetric. We make different deductions in each dictionary. All right, now we go back over to d out. So the objective function in d out is this. It's the constant v plus this linear combination of stuff. But we know that as far as the dictionary was concerned, when the dictionary was created, so when the pivot happened that brought us to this dictionary, obviously all of these non-basic variables were set to 0. So, in practice, the objective value is actually just this. This summation is only used to help us choose pivots and things. On the other hand, we'll see in a minute, we do need to use these coefficients for something in this proof, not as part of the simplex method, but to prove a point about something else. Similarly, every row of the basis is nominally this, so it'll be a constant plus some linear combination. But of course, in practice, these are all set to 0. So, that's one of the reasons we like dictionaries so much, is we can just, read off the value of these basic variables by just looking at the constant column. So that's true, but we're going to see in a minute that we want to employ that insight from earlier. So obviously I wouldn't have, reviewed the basic properties of a dictionary if there wasn't a however coming. So the however is, and I'm going to scroll, sorry. The however is, what if we apply this insight from back here? The insight where I said, let's take a non-basic variable and, external to the simplex method, let's just set it to a non-zero value and see what happens. And of course, we need that in the proof. So we're going to do that. In the dictionary d out, we're going to consider what happens if I take some variable, just put a box around this. If I say, let's let y be greater than 0, and then set xe to have the value y. We're not actually going to, that won't change our dictionary. We're going to do that to prove a point about something. So if I set xe to equal y, what does that tell us about the objective function? Well, the first thing it tells us, if I do nothing else, so every other non-basic variable is still equal to 0. Well, now the objective value will be v plus pe times xe, which is pe times y. Similarly, the value of each basic variable will be a constant. So if I've got some other basic variable xi here, so it's b sub I plus a bunch of stuff plus aie times xe. All of these basic variables will now have the value bi plus aie times y. And that's what this is getting at here. So if I set xe to some arbitrary positive value, and it's going to be very significant that I haven't specified any particular positive value yet, if I set it to some value y is greater than 0, then the objective value becomes this, because everything else is still being, every other non-basic variable is still 0. And every basic variable in d out, so every member of the basis b out, is going to be set to bi times aie times y. Okay, so why do we care? Well, here we go. We now know enough about both dictionaries that we can begin employing the same thing we did back on slides 36 and 37, where we begin taking information from one dictionary and subbing it into the other dictionary. And as you can see, this is already getting a bit ugly looking, and it's not going to get any better for a couple more slides. We're going to do this with the goal of deducing a few more properties about what has to be the leaving variable in each dictionary, and that's what's going to take us to a contradiction. Okay, so the first thing to observe is these two dictionaries that I've created here are referring to the same system of equations and indeed exactly the same vertex of my polytope. So when I say that zeta equals this, and when I say zeta equals this, I'm actually saying that this equals this. That's an identity. And the same would be true of basic variables, but we can get by with only the objective function. Okay, so we know that the two zetas are equal. We have chosen some arbitrary y, which is greater than 0, so it's not equal to 0, but we haven't decided on a particular value. And we know that that means that in the dictionary d out, the objective function equals this. We also know that we can do the same thing we did on slide 36 or 37, and I'll revisit that. So back somewhere around here, yeah, there it is. Sorry, it was this slide. What I observed was that W2 on the left dictionary, if I set x3 to equal y, W2 equals 0 minus y. I then, because I want to compute how that applies to this expression for the objective function, I just sub that in for W2. I'm going to do the same thing in the proof. I know what the value of each basic variable in d out looks like if I set xe to be equal to y. So for example, xi would equal bi plus aie times y. So I know what that is. If I want to evaluate this objective function with the same change that I made over here, what I do is I take each basic variable from over here and I sub it in. I sub in this expression in the objective function. So I'll clean that up in preparation to come back to this slide in a minute. Okay, so that's what I'm planning on doing here. So I already know that zeta out is equal to v plus pe times y. And what I'm going to do, the reason that I made this more convenient expression for the objective function for zeta in is because I don't want to have to think about which variables are basic and non-basic. I know that some of the basic variables in d out will be non-basic variables in d in. I don't know which ones, and I don't actually have to, because I've defined this new summation where the objective function is defined in terms of every single variable, with the understanding that the coefficient for the basic variables is set to 0. Okay, so if I write that out, what does that give us? Well, what I've actually modified here, the objective function was previously 0. So before I made the modification to xe, the value of the objective function was 0, period. And so the change that will happen if I modify xe to be equal to y is obviously I will change the value of associated with xe. So the objective coefficient for xe is qe. And I've just changed xe to equal y. So of course, the objective function will be modified by this amount. Keep in mind, qe could be 0, because I have no way of knowing necessarily whether the variable xe is a non-basic variable in d in. So notice if I go over here, xe is the entering variable in d out, but I actually don't know yet where xe is over here. I don't even care. I just know that if I modify xe, I have to have some way of reflecting that modification in din. And I do that with this, because I know that qe will equal 0 if xe is not a non-basic variable. So the modification of the objective function is this, the modification to xe itself, plus these are the expressions for the basic variables in d out. And that's that trick I showed from somewhere around slide 35. I need to sub in the modified value of each basic variable into the objective function for d in. And so I do that by deriving it, and then of course the derivation is b sub, this should be a j e, not a I e. So the objective coefficient for variable j, for every variable in the basis of d out, because those are the only variables that could have changed as a result of changing xe, I have to also add in the effect of modifying that. So q sub j times the new value of that variable. Okay, so that's where I got this from. So I now have these two equivalent formulations for the same objective function. This and this. And I know that they're equal. So I can state this identity here. So it's just putting each objective function on one side of the equal sign. And then I rearrange it a bit, so I try and factor a y out. So the first thing I'm going to do is over here on, I just get rid of the these because I don't need those. And then I've got PE times y, and then I factor a y out of, so I split this into two summations, and I factor a y out of the part of the summation that involves this. And so you can verify the algebra yourself later if you want, but you end up with this. Y times this thing in brackets plus this extra summation here. And this is the step the proof is about to take is actually very clever. When I encountered it while making these slides, I grimaced because I thought it was really, there was something about it that just felt like it could have been described in a more conceptual way. The author just sort of says, oh yeah, there's this trick you can use here, just use it, without really explaining what was going on. So I'm going to do one more rearrangement, which is that I'm going to put all the terms involving y on one side. So I end up with this. So if I move this term over here, and then I factor out a y, I get this relationship. So I'm going to call this y times term A equals term B. First observation. Nowhere inside of term A or B do I actually use y for anything. So in a sense, with respect to y, term A is a constant, and so is term B. The other thing I should observe is that this identity holds regardless of what value I chose for y. All I said was y is greater than 0. I didn't say specifically what value y has, and yet I derived this identity that has to hold no matter what value I chose. Which means if I wanted to, I could choose two different values for y and then draw a conclusion from that. So if we call this term A and this term B, I'm going to rewrite what's down here to prove my point. So what if y equals 1? Well, in that case, I'm saying that 1 times A equals B. Okay, so what if y equals 2? Well, in that case, 2 times A equals B. And if I look at this system of equations, what I'm actually saying is 1 times A equals 2 times A. And what conclusion can we draw from that? Well, obviously, that means that A has to equal 0. I mean, there is no other option. Term A must equal 0. Wait a minute though, if term A equals 0, then 1 times A equals 0, and that means that B also equals 0. All right, which I think this is a clever trick. I don't know why it has to happen here. This is a clever trick to see in a proof. It feels sort of out of place here because it's just some random property of real numbers. It's a basic algebraic property. I sort of feel shorted a bit because I don't recall ever having seen this trick used in a proof, as far as I can remember, going back years and years and years. It's a very clever trick. I feel like it doesn't do the trick justice that I'm only seeing it actually show up in a proof now. So I can assert from the fact that y was an arbitrary value that both this and this must equal 0. And now we're entering the home stretch here. Now I'm going to use these two things and make some deductions. I now know that this sum equals 0 and so does this one, and I can make some deductions based on that. So I'm going to start with this. We know about, we should understand PE and QE, so I want to talk about, I guess I better go back to this. Okay, so we've already, talked about what PE is. So in my dictionary D out, XE was my entering variable. And we know that because it was the entering variable, PE, the coefficient on XE, has to be positive. So that's one thing we can observe. Okay, so I know PE has to be greater than 0. Okay, so that's deduction number one. I guess I'll write it down under deduction one. The next thing that we have to consider is, so xe is the entering variable in D out. So xe was chosen as the entering variable over here. But what about over here? Could what is the status of xe over here? And we have to consider a few things. So one of them is xe does enter or leave at some point during the cycle, because obviously xe is the entering variable at this dictionary during the cycle. We chose at the beginning of the proof, we said xd is the highest numbered vertex that ever enters or leaves. And that means that we know, because xe and xd both enter and leave, e has to be lower numbered than d. It has to be. xe has to have a lower number. Okay, what does that tell us about how xe behaves over here? Well, let's see. xe is either basic. I mean, maybe xe is a basic variable in d in. That's possible. Suppose xe is non-basic. I guess that's also a possibility. If xe is non-basic, that puts it sort of in here. And that means it'll have an objective coefficient qe. Could this objective coefficient be positive? And the answer is, well, no, because xe is lower numbered. If the objective coefficient qe was positive, then xe would be the entering variable. That would be a contradiction, so we can't allow that. So that means the objective coefficient for xe has to be either a negative or zero. We think of it as being zero because remember that we defined an objective coefficient for every variable in D in. And we know that if the variable is basic, the objective coefficient is equal to zero. But we know that in any case, the objective coefficient QE will be either negative or zero. Okay, so that would be deduction number 2 here. So QE is less than or equal to 0. It has to be, because if it's greater than 0, then XE was the entering variable in D in, which is a contradiction. Okay, so what do we know? Well, we know that PE is greater than 0, and QE is less than or equal to 0. And what does that tell us about this? PE minus QE. Well, it's a positive number minus a negative number, which means this whole thing has to be greater than 0. Because PE is greater than 0. So what does that tell us about this? Well, let's see. This positive number minus this thing has to equal 0, which means I think that means this has to be greater than 0. And that is our third deduction. So the only way where this equation comes out to equal 0, assuming that this whole thing is positive, is if this is positive. And that means that this whole summation is greater than 0. Now, it's a summation, which means we can't necessarily make assumptions about all of its terms. So just because the summation comes out to be positive doesn't mean that every term is positive. So my deduction is going to be a very, very, very humble claim, which is that if the summation is positive, at least one of the terms of the summation has to be positive. Just one. I don't care which one. There has to be some index that's positive in this summation, where this whole term is positive. Let's call that index R. So the summation is over the basis of D out. So the basic variables of our dictionary D out. There is one index in that basis such that this whole thing is positive. So that is to say, there is one basic variable, we'll call it XR. There's one basic variable in D out such that this whole thing comes out to be positive. Okay, let's go add that to it. Let's update our diagram with that. Okay, so there is a variable XR in the basis here. We don't know that much more about it. I guess we know that there is going to be this thing ARE times XE. So ARE could be 0. We don't know what it's going to equal. I guess there's also BR here. And we're going to get our contradiction with the relationship between XR and XD. Okay, so we'll go back over to where we were. Our deduction was that this product here, which is the product of the objective coefficient of XR in D in and ARE, so, oh boy. So here's ARE. It is sitting in the dictionary D out. And the objective coefficient, I'm going to move this. Plus QR times XR. So the objective coefficient of XR in D in is called QR. And we might already sort of know where this is going. We use the same trick already with XE. We can say certain things about what QR can equal. So those are the two variables we're concerned about. This thing and this thing. And I told you the proof was going to be nasty. And maybe you didn't believe me. Hopefully you believe me now. But we are almost there. So we know that this product is positive. By my assumption that if this summation is positive, there has to be at least one positive term. We'll call that term R, and then this term has to be positive, strictly positive. So the key there is if we look at this thing, we have a product that comes out positive. And this tells us two things. So one, if it's a product and it comes out positive, both of these things can't be equal to 0. Clearly, if either of them were 0, the product would be 0, and it's strictly positive. Now, we don't know that both things are positive. They could either both be positive or both be negative, but we know that they're not, that neither of them is equal to 0. Okay, so the deduction implies a couple of things. One, we know that because this summation was over the basic variables of d out, that xr is a basic variable in d out. I already drew that on my diagram from a few slides ago. But the other thing it implies is if we know that q sub r is not equal to 0, that means that xr has an objective coefficient in d in, because the q's are the objective coefficients for d in. So here we go. We'll head on back to this. Okay, so this thing, q sub r, is not equal to 0. Okay, so now we're going to have to think about this a bit because, wait a minute, we know that xd is the entering variable. I should actually write that. Maybe I should. Okay, so xd enters. And then xl leaves. And over here, we have, xe enters and xd leaves. And these assumptions, these are the assumptions we made when we defined d out and d in. So we said, let d out be a dictionary where xd leaves. Let d in be a dictionary where xd enters. And similarly, define xe to be whatever the entering variable in d out is. So if we discover later that xe doesn't enter or xd doesn't leave, then we have our contradiction. That's what we're going for here. And we're going to prove it with this. We're going to prove xd isn't the leaving variable. And we're almost there. So we know that in d in, our variable xr has a non-zero objective coefficient. And the question is going to basically be, what can we do to make sure that xr wasn't the entering variable? Because our assumption was that xd is the entering variable. So we'll head on over here. Okay, so we know that xr is non-basic because it has a non-zero objective coefficient in d in. We also know that xr is basic in d out because it has we selected it to be part of the basis of d out. And actually, sorry, I missed a point last time I visited my diagram here. There's one other point I have to make. So earlier, I'm going to write this a little bit higher up because it's a bit of a mess. Earlier, I pointed out that we know that e is less than d. So why is that? I chose xd to be the highest numbered variable that enters or leaves during my cycle. And we saw xd both enters and leaves, and so, okay, whatever. We also noticed that xe enters at some point during my cycle. That means that xe leaves at some point during my cycle. And by the definition of xd, I know that xd is the highest numbered variable that enters or leaves. That means that e has to be a lower number. I'm going to make the same argument for r. So xr is in the basis in d out and out of the basis in d in. So it's non-basic over here, it's basic over here. What does that tell us? It tells us that I don't know when this happened, but at some point xr enters during my cycle, and at some point xr leaves. Otherwise, how would it end up switching between basic and non-basic? That means xr is a variable that enters and leaves during my cycle, which means the same thing applies to r. So r has to be a lower number than d. Otherwise, my assumption that xd was the highest numbered variable is somehow false, which doesn't make sense. By definition, xd is the highest numbered variable that enters and leaves. Okay, so if r has a lower number than d, then I know that q sub r is less than 0. It has to be, because if q sub r was greater than 0, xr could be the entering variable. And if r is less than d, Bland's rule would have chosen xr. So the only option that I have is that q sub r has to be less than 0. And we're almost there. So the next thing we have to assert is, wait a minute, so if q sub r is less than, I guess we also have that xr equals 0. I'll get to that in a minute. And so we're almost at our contradiction. So we know this. We know that this product, QR times ARE, is greater than 0. And I think I can illustrate the rest on the diagram, because I'm getting sick of flipping back and forth. So here's the property we want to, here's what we were able to deduce. QR plus times ARE is strictly greater than 0. We now know that Q sub R is less than 0. So Q sub R is less than 0. Ugh. What does that tell us about ARE? Well, the product is greater than 0, which means I think it's reasonable to assume that ARE is less than 0. Well, that's interesting. One last point to make. So we know that XR and XD and also XE, they enter and leave at some point during my cycle. By one of the insights from earlier, we actually know that that means that their values, because all of the pivots are degenerate, the value of XR and the value of XD has to be 0 during the entire cycle. So certainly when they're both in the basis together, they both equal 0. And we now have everything we need to show our contradiction. So XR is a lower numbered variable than XD. We know that ARE is less than 0. We know that ADE is less than 0. So we've now gotten to the end stage here. XE is my entering variable. What is the leaving variable? Well, let's see. So we only allow something to be a candidate for the leaving variable if the coefficient is negative. But wait a minute, both ARE and ADE are negative. Additionally, both of them have the value 0. In other words, if we're doing the simplex method, this puts the bound XE is less than or equal to 0, and so does this. So both of these put the same bound on my entering variable, both XR and XD. And that means that both of them are candidates to be the leaving variable. XR and XD could both be the leaving variable from this dictionary. Now, we defined that the leaving variable was XD, but what does Bland's rule choose? Well, let's see. Bland's rule says if you have more than one candidate for leaving variable, you always choose the lower numbered one, and that one is XR. And that finally gives us a big fat contradiction, because XD was defined to be the leaving variable, and we showed that Bland's rule wouldn't choose it. And so then we look back and say, okay, we have a contradiction. What did we contradict? And I noticed, I pointed out even at the earliest stages, from this point onward, starting at this slide, every single assumption I made was a deduction. It was just, okay, we know that there had to have been at least one pivot during the cycle. Therefore, at least one variable entered or left. So XD is the highest numbered such variable. That's not an assumption, that's a deduction. That has to be true. It's reasonable that at least one pivot occurred, at least one variable entered or left. Therefore, let's decide that XD is the name of the highest numbered one. Everything else I did was basically either some sort of arithmetic deduction or algebra. The only actual assumption that I made during the entire process was that there was a cycle. And that's the assumption that I've contradicted. So I said, suppose a cycle existed. I proceeded forward through a nightmarish bunch of notation and algebra, and I showed there was a contradiction, and therefore we know that the cycle didn't exist. And therefore we can prove that Bland's rule does not cycle. So via quite a character building exercise, we can show that Bland's rule doesn't cycle because we arrived at that contradiction. And now finally, we have been able to prove that if I use Bland's rule to select my pivot, the simplex method is guaranteed to terminate. It does not cycle. And so we can now actually show, we can talk about this fundamental theorem of linear programming. Because we established in the last lecture that either the simplex method cycles or terminates, I mean, really what we're saying is either it terminates or it doesn't, and we now showed that it can't cycle, so it has to terminate. Because we have that, we can use what the simplex method gives us to state and prove this, the fundamental theorem of linear programming, which says for any linear program in standard form, and the footnote is observing that if you give me pretty much any linear program, I can put it in standard form, except for weird-looking things like strict inequalities, which we don't really count as linear programs in this course. For any linear program in standard form, we can expect these three things to hold. First, if there is no optimal solution, the only reason that that could occur is because either the LP goes to infinity or because there are no feasible points. Okay, so suppose that there is at least one feasible point. Now, I mean, it could still be unbounded, but suppose there is at least one feasible point. If there's at least one feasible point, there is a basic feasible solution. Now, remember that a basic feasible solution is, you can read that to mean either a vertex of the polytope, or you can read it to mean a dictionary that is feasible. So a basic feasible solution is a solution that could be realized by a dictionary. Early on, we were talking about the geometry of linear programming. I sort of illustrated, I sketched out this point that the optimal solution of an LP always occurs at a vertex of the polytope. And I said, we can't quite prove this yet. Okay, here we are. We're proving it now. If there is a feasible solution, there is a vertex of the polytope. So if the polytope is non-empty, it has a vertex. And number 3, if there is an optimal solution, so if the LP is feasible and bounded, there is a basic optimal solution, a solution that occurs at a vertex of the polytope. That's the theorem, the fundamental theorem of linear programming. And I can show you the proof. It's this. It turns out the simplex method, now that we know that it works, actually provides us everything we need to prove this theorem. So the key here is, because we know that I can start from any linear program and the simplex method will terminate, and I also know that what it gives me when it terminates can be used as a certificate for one of the 3 possibilities, unbounded, infeasible, or optimal, that's sufficient to make the case for this proof. I'm going to go in the same order as the bullet points, but actually, in a sense, these 2 factor into how I would demonstrate these points. But that's just an editorial remark. So you hand me an arbitrary LP. Okay, well, if it's not initially feasible, I will use the simplex method to solve the auxiliary problem, minimizing that auxiliary variable omega. We know that if the simplex method finds an optimal solution to that problem, where omega is equal to 0, then I can convert the resulting dictionary to a feasible solution to the original LP. But suppose not. Suppose it gets to a minimum where omega is greater than 0. And remember that because in a minute I'm going to show off that if you start on an LP, the optimal dictionary you come up with is a certificate that you cannot improve the objective value further. If the simplex method gives me this terminating dictionary where omega is greater than 0, that is a certificate that it is impossible to make omega any smaller. If omega can't be made smaller, as you've seen looking at these auxiliary problems, that means that there is no feasible point to the original LP, unless you can find a way of setting omega to 0 and coming up with a feasible assignment. So if we get to a point where omega can't be minimized, but it's still greater than 0, it can't be made any smaller than some positive number, then the original LP is infeasible, and we have a certificate of that fact. Suppose that the auxiliary problem terminates and omega does equal 0. We saw in a few lectures ago that it's possible to convert that optimal auxiliary dictionary to a feasible dictionary for the original LP. That is allowing us to realize bullet point number 2, which is if there is a feasible solution, there is a solution corresponding to a dictionary or a vertex of the polytope. So this is saying if you are able to get omega down to 0, we have a mechanical procedure to produce a basic feasible solution, to produce a feasible dictionary for the original LP. Okay, now finally, suppose that we have a feasible dictionary for the original LP. So we found one basic feasible solution, and I want to assert that the only other options are either unbounded or optimal. Well, I will run the simplex method on that feasible dictionary for the original LP, and the simplex method won't cycle because we proved that it won't. And as a result, it will terminate. And there are only 2 ways it terminates. It either terminates because it finds something unbounded or because it finds the optimal solution. Let's think about why we know that in both cases it's right. So suppose it determines that the LP is unbounded. Well, that means it reaches a point where the objective function is equal to, so we've got some variable xi that's unbounded. So it has a positive objective coefficient, and there is nothing in the dictionary, there's no basis row that constrains xi. So I can increase xi as much as I want and make the objective function as large as I want. Because I have this dictionary with all these basis rows, and I can see, like you can actually look at that dictionary and observe that none of them constrain xi, that is a certificate. That is proof that xi truly is unbounded. And in turn, that the objective function value is unbounded as well. So if the simplex method reaches that terminating point, we have proof that the LP can be made, that the objective function can be made to go to infinity. And then finally, the case that we always care about the most, suppose the simplex method terminates because it reaches the optimal dictionary. in the expression for the objective function in the optimal dictionary, we will always have every coefficient negative. And we know that because all of the optimization variables are constrained to only be 0 or positive, that is, they can't take on negative values, if we find a way of expressing the objective function where every coefficient is negative, and there's this constant here, that itself is proof that we cannot make the objective function any larger, because there is nothing we can do to any of these x variables that will increase that objective value. And so that is a certificate. If we find a dictionary where this is observed, that is a certificate that we have found the optimal objective value. And so we were able to use what the simplex method produces, along with the fact that we are guaranteed it will produce one of those outcomes, to prove the fundamental theorem of linear programming. What I want us to appreciate is not only that finally it's over and we've done that, but that it's interesting that the proof of the simplex method working and the proof that linear programs are solvable are sort of intertwined. We designed the simplex method around properties of linear programs. We proved the simplex method, we proved that it was correct using, let's say, Bland's rule, using properties of linear programs, and then we turned around and proved some properties of linear programs using the simplex method that we just proved to work. So what are we going to do next? Well, we're going to spend some time talking about the fact that now that we know that the simplex method terminates in a finite amount of time, maybe we should ask, hey, can we make that a small finite amount of time as opposed to a large finite amount? We're going to talk about performance and complexity of the simplex method. And then we're going to turn around and start talking about some theoretical stuff related to the theory of linear programs in general, in particular, a massive thing called duality, which requires, of course, that we, prove linear programs have solutions like we've done just now before we can really address it.